What's the difference between your left and right foot? They look similar, yet putting your right shoe on your left foot, or vice versa, is super uncomfortable. Left and right earbuds look similar too, but whenever I put an earbud in the wrong ear, I instantly regret it.
Both of these objects have a left and right side and can be described as chiral. An object is chiral when it is not the same as its mirror image.
For example, the mirror image of my left shoe is actually my right shoe, and no matter how I rotate, flip, or move my right shoe around, I can't get it to look the same as the left shoe. But an object that doesn't have a left and right side like a pencil is identical to its mirror image, which makes it achiral, meaning not chiral.
Chirality isn't just some obscure concept, though. Almost all of nature is chiral.
Hands, feet, paws, plants, shells, and proteins are all chiral. And when a molecule is chiral, like this one, its non-identical mirror image is called its enantiomer, which comes from the Greek word enantio for opposite. Enantiomers have the same molecular formula and chemical connectivity, but differ in the spatial arrangement of their atoms. So just like my shoes, no matter how I move these enantiomers around, the closest I can get to identical is a mirror image. And since many molecules in the human body are chiral, like proteins, enzymes, and receptors, our bodies recognize enantiomers as two distinct substances and respond to them differently.
For example, the two enantiomers of a molecule called carvone have two very distinct scents.
One smells like caraway seeds and the other like spearmint. This is because the two enantiomers of carvone fit into different chiroreceptors in your nose, so they smell different to us.
Similarly, the two enantiomers of a molecule called linalool
smell like sweet orange and lavender. And when it comes to medicine, sometimes only one enantiomer is responsible for a drug's desired activity, while the other is less active, inactive, or even responsible for negative side effects, like in the case of thalidomide.
In the 1950s and 60s, a drug called thalidomide was prescribed to many pregnant women as a morning sickness medication. One enantiomer of thalidomide is an effective sedative that delivered the desired effect of the medication. No problem, right? Wrong. What the drug manufacturers and researchers failed to discover was that the other enantiomer of thalidomide could cause serious birth defects. Thalidomide wasn't manufactured to just isolate one of its enantiomers. It was actually a mixture of both, resulting in over 2,000 cases of serious birth defects. Happily, today's drugs are much more thoroughly tested and can even be manufactured to isolate just the enantiomer that is not responsible for negative side effects. All this to say, the importance of understanding chirality and its effects will continue to be seen in chemistry, biology, and medical research. The mistakes of the past can and will be used to inspire the progress of the future.